frustration that I became a mathematician, and I recall the reason why. So it turns out he was interested in many things. He was also, he loved history, and he was debating between majoring in history and majoring in mathematics. And you can tell from all his writing how literate he is, and what a great culture he has. Anyway, I was about to deposit my punch cards in the honors history bin, because in those days you didn't sign up online. You had a computer, but you had, maybe some of you have heard about punch cards, so you sign up to a course by having punch cards saying, I sign up to the history major. And then he was thinking, if I do study history, in 10 years I will have forgotten how to use a calculus properly. If I take mathematics, I shall still be able to read competently about the War of 1812 or the Papal Schism. So he chose, luckily, to be a mathematician. The inescapable reality of objective mathematical knowledge is still with me. Nonetheless, my view then of the edifice I was entering is not that close to my view of the one I inhabit 40 years later. So he evolved very, very much from pure mathematicians to traditional applied mathematicians who still believe in the dogma of proving everything into an experimental mathematics. I also know when I became a computer-assisted fallibilist. So fallibilist is something Imre Lakatos, a professor, a philosopher, coined, that nothing is certain in this world. Everything is in doubt. Even the proof of the Pythagorean theorems. Nothing is sure in this world. Maybe Pythagoras made a mistake. Maybe all these people who check the proofs made a mistake. Maybe there are cases in the literature, not so big, but that people believe something to be true. So it's called fallibilism. Reading Imre Lakatos' proofs and interpretations a few years later, while a very new faculty member, I was suddenly absorbed from the grave sin of error. And I began to understand that missteps, mistakes, and errors are the grist of all creative work. So mistakes are underrated. You learn from your mistakes. Erroneous paper, many erroneous papers are much more important, much more significant than many true papers. If you have a good idea, even if you have mistakes, it could be better. The book has doctorate posthumously published. Okay, let me go on. Today, we appreciate fine proofs and aim to produce them when possible. I no longer view proof as a royal road to secure mathematical knowledge. So you can get secure mathematical knowledge by other means, by experimental math. And then he goes on. Let me read more excerpts. He defines his dictionary. He also has a nice dictionary of mathematics he wrote with a collaborator. And the definition of mathematics is there. Mathematics noun. A group of related subjects, including algebra, geometry, trigonometry, and calculus, concerned with the study of number, quantity, shape, and space, and the interrelationships, applications, generalizations, and abstractions. That definition is taken from dictionary Borowski and Borwein. It's also a nice book. It's a paperback history of a dictionary of mathematics that is very concise. But then he goes on to talk about the philosophy of experimental mathematics. Let me read now. My questions. What constitutes secure mathematical knowledge? When is computation convincing? Are humans less fallible? What tools are available? What methodologies? What of the law of small numbers? Richard Guy, who went on 100 in 2 weeks, famously wrote an article, the Strong Law of Small Numbers, where he gave many examples of sequences that agree to quite a few terms, sometimes 15 or 20, only later on to deviate. So this is the weapons in the hands of the purists who say you cannot trust experiments, you have to prove everything for every end, so there is a way around it. but you have to be careful, of course. This is presumably more controversial in the formal proof sense. And then he describes the 4 kinds of experiments that the British Nobel Prize winner oncologist Peter Medawar. So he talked about experiments mathematics. So he described the 4 kinds of experiments that Peter Medawar. The first kind is a Kantian from Immanuel Kant. The Kantian experiment, sorry. So he describes Sir Peter Medawar 4 types of experiments. The first one is Kantian. This is really completely mental and mathematical. It's not really an experiment. Then the prototypical experimental science is Baconian. So you make an artificial scenario to see what's going on. You don't just go to nature and see what's going on. You want to study something, so you make an experimental apparatus and you do it after Roger Bacon. And then you have the so-called Aristotelian experiment. This is just checking what you already know, just confirming what you already know. And finally, the most important one, the Galilean, from Galilei. And this is the most important type of experiments. They decide between 2 options. You have 2 options, one or the other, and this is deciding experiments between the 2 options. For example, when Eddington tried to confirm or refute Einstein's theory of relativity by looking at the solar eclipse, there was an example of Galilean experiment. So Einstein is right or wrong. So, and then that's the best type. And then Borwein goes on to say that that's very nice, but it's hardly ever possible. And then that's the other. And then he goes on, our experimental methodology. So he coined a new word. It's a methodology, it's a compound. It's a hybrid. Experimental methodology. Despite Picasso's complaint that computers are useless, they only give answers, the main goal of computation in pure mathematics is arguably to yield insight. So this is also paraphrasing Niels Bohr's colleague Hamming, right? Is that your colleague? Mm-hmm. Yeah. So he said the purpose of computation is not numbers, is insight. So he echoes this. This demands speed or equivalently substantial micro-parallelism to provide answers to relevant questions. Algorithms reason for believing that one has at hand a tractable, unavoidable set of configurations. That's the 4-color theorem. So he gave some examples of the famous computer-assisted proofs that should be trusted, even though the detractors of computers say you cannot trust computers. Computers always have bugs, both software and hardware. And with all due respect, humans have much bigger bugs. And of course, nothing is certain, but you have this. So then he went on and gives nice examples. Finally, let me go to, not yet finally, almost finally, one of his latest papers, only written a few months before he died. It was submitted to the Aladi 60 conference. Adventures with the OIS. So Borwein, being the guru of mathematics, was a great fan of the online encyclopedia of integer sequences. And we are lucky to have the founder and still president and maintainer of this amazing site. One of the greatest tools in experimental mathematics, and John Borwein loved it. And he wrote a whole article that I strongly recommend that you download from the internet, called Adventures with the OIS. And let me read it from the introduction. What began in 1964 with a small set of personal file cards has gone over half a century into the current wonderful online resource, the Online Encyclopedia of Integer Sequences, OIS. And then section 1.1. Introduction to Sloan's On and Offline Encyclopedia. I shall describe 5 encounters over nearly 30 years with Niels Sloan's online encyclopedia of integer sequences. Its brief chronology is as follows. In 1973, a published book with 2,372 entries appeared. It was based on file cards kept since 1964. In 1995, a revised and expanded book by Sloan and Simon Plouffe with 5,488 entries appeared. Sometime soon after the www went public, the OIS went online with approximately 16,000 entries. As of November 15, 2015, the OIS had 263,957 entries. And what is it now?
276,692.
And then he goes on, I really recommend the book, The OIS in Action. And he gives examples from the Banach sequence and how the OIS inspired interesting and sometimes deep research by finding connections between this. So I really strongly recommend this. Finally, another paper we wrote fairly recently with the future of mathematics that I also recommend very much. So let me read you just a few excerpts and then I'll let you go. The bigger picture. It is generally the way with progress that it looks much greater than it really is. The world will change. It will probably change for the better. And then he goes on to talk about the future of mathematics. Some things will not change much. Certainly there are areas being deeply studied that were not in 1965, but in broad brush, despite Gödel and Turing, the nature of mathematical research has changed surprisingly little over the last half-century. We do collaborate more, but most researchers take stunningly little advantage, even of tools like Skype. And then, pressure to publish. This is unlikely to abate, and this is a big drawback. People publish too much because they have the pressure. And then, the Matthew effect or principle. This is sociologist of science Robert Merton's apt dictum that to those who have shall be given. And yet the rise of the blogosphere makes it all the easier to focus on a few star names. Thus polymath quickly becomes synonymous with Gauss and Tau. So you have these superstars and they get more credit than deserve, and then they have the complement that get less credit than deserve. So this is an unfortunate thing. And then he takes issue with Dieudonné, the great Bourbakist, about short-sightedness. They excluded from the introduction to mathematics lots of areas they considered unimportant, like applied math and probability. And so I don't have time to get everything, but I strongly recommend. So I hope that I gave you a glimpse of the great heritage of what Jonathan Borwein did. He wrote enough paper, more than 430 papers, enough for somebody who would have died in 100 years. So he did fulfill his quotas, even when he died so young, at 65. He published enough but it's not only the quantity, it's the quality, and the sum, it's much bigger. The sum of the parts is very, very, very big. But the whole, what he did, his whole vision is still bigger, and he will stay us forever. So being the prophet, the icon, the messiah of experimental mathematics, he is immortal, so he only died physically, but spiritually he is forever immortal. Thank you very much. Thank you, Pam.
You know, he was videotaped when he came to London.